presentation. Okay, so I'm a teaching and research assistant at the University of Southern Brittany in Van, Britain. So I will be presenting quantitative recurrence results that we obtained for Z-extension of three-dimensional axiom A flows. I will start by giving a motivation on quantitative recurrence. In fact, quantitative recurrence is a study that have been recently these days, and it's defined by estimating the first return time of a dynamical system into a small neighborhood of its starting point. So in general, what's a dynamical system? Preserving a probability measure. It's a space, measurable space X, B, with a probability measure mu, and T, it's a measurable transformation from the space X into itself, which preserves the measure mu. It means that the measure of, if we take a measurable set, so the measure of the pre-image of the set, it's the measure of the set itself. We can also say that mu is invariant by the transformation T, and sometimes we can say that mu is T invariant. So what we consider is dynamical systems where the conclusion of Poincaré theorem is satisfied, which means, so if you have a probability measure preserving dynamical system, if you take a measurable set with a positive measure, so for almost every point in this set, there will be a time such that T and X is in the set. In fact, for almost every time we know by the conclusion of Poincaré theorem that we will return back very close to the starting point X and we will enter the set. So we know that the orbit of the system will return back. And the question will be, what is the time needed to return? So for example, if you take a point X in the space, we want to see the orbit of this point. So, but by the transformation T, from X, you apply T, Tx, then T2x, until, and this is this sequence of iteration, it's the orbit of X. And we want to study the behavior of this orbit. So if we take an epsilon neighborhood of this starting point X, a ball of center X radius epsilon, so by the recurrence, the Poincaré recurrence theorem, we know that there is a time, a moment n, where the orbit of X will enter for the first time in this neighborhood. At this moment, this is what we call the first return time. And so we define for all X, the first return time of the orbit of X into this ball of the center X radius epsilon by tau epsilon of X, which is the infimum n, such that Tn of X is in the ball. So the goal is to study the asymptotic behavior of this return time, tau epsilon of X, when epsilon goes to 0. In fact, this motivation is in general, if we have a discrete case, because you see the map T, we have X, Tx, T2x, T and X, we are studying an integer. So, but in this talk, we will consider the case of flows. In fact, we will extend the study. There have been many results in this case where we have discrete case. So we extend the study to the continuous case with dynamical system with continuous time. And precisely my work is where the measure that we consider is infinite. So more precisely, we consider Z-extension of Axiom A flows. So the flows is the continuous time, and Z-extension, it will give an infinite measure. We will see how. So that's to describe my model. I will just start to say what is the formal definition of a flow in general. And to give the definition of axiom A flows, I need to give a notion of hyperbolicity. And then this flow, this axiom A flow, will be represented by a suspension flow. We will see how. And at the end, we will describe what is our model, the Z-extension of axiom A flow. So, in general, if we have a Riemannian manifold M, the definition of a flow, so it's an application from R to M on M, which is a smooth manifold. So with a time t position x, we have gt of x. So at time 0, we have g0 of x equal to x. And if we have at time s, gs of x, and we apply gt to this gs of x, we have gt plus f of x. And this map will be of class C1. So as we said, to introduce the axiom A flows, I have to give a notion of hyperbolicity. So if we consider our flow, GT, which is defined on a three-dimensional manifold, so we say that a compact set lambda in our manifold M is hyperbolic set for our flow if lambda is invariant by our dynamics, by the flow GT, and moreover, we have a splitting of the tangent space at X in this sense. So we have that the tangent space is decomposed as follows. So we have the vector space, which is generated by the vector field. And then we have the stable subspace, which is the vector space, where we have a uniform contraction under the differential in the future, and the unstable space, where we have the uniform contraction but for the differential but in the past. Okay, so to explain this, maybe this picture is better. So if we consider a point x in lambda in our set, so we have at time t equal to 0, we have our vector field. So this is the direction of the flow. And these lines correspond to the direction of the vector field. At time t, we have this vector, we have gt of x, we have the vector field as gt of x. And we see here the stable direction. So at the point x, we can see that the stable direction is it's contracted in the future, and the unstable direction, it's contracted but in the past. Okay, so and also we can see that with the stable and unstable directions, we can see that it's identified by a plane which is codimensional with the flow. Okay, so that's it. And for all x in lambda, there exists stable manifold, a local stable manifold, and a local unstable manifold at the point x, such that the point x is in this stable and unstable manifold, and we have that the stable subspace and unstable subspace are the tangent spaces for the local and stable and unstable manifold respectively. Okay, so we have these subspaces here are tangent spaces for locally stable and unstable manifolds. This is the notion of hyperbolicity. In fact, before moving to axiom A flows, for example, we have the Nasab flows. The Nasab flows, in fact, the hyperbolicity will be for all the manifold. So the whole manifold is hyperbolic, and this will give an Nasab flow, which is generalization of axiom A flows. So for axiom A flows, the condition of hyperbolicity will be on a smaller set. It will be a set called non-wandering set, and that's what I will introduce. So in fact, we say that a point X is called non-wandering point if we take a point X and we take a neighborhood of this point X. So for a time t positive, the neighborhood revolves with time, and you can always find a time tx depending on x, which is greater than t, such that it will meet the initial neighborhood. So there are some points which will return back to themselves. So these are the non-wandering points. And if we note by gamma omega gt the set of all non-wandering points of our flow, so this flow, it will be an axiom A flow if the set of all non-wandering points of it is hyperbolic and the periodic orbits are dense in this set. As an example of an axiom A flow, just an example that I use just to present geometrically that shows to understand. So this is a manifold of negative curvature, which is an example of an axiom A flow. It's the geodesic flows on the surface immersed in the torus of this equation. So just an example to see. So for axiom A flows, in fact, this is very interesting now to study the return times. So for axiom A flows, there is always a Markov family. In fact, a Markov family is a finite collection of rectangles. These rectangles, you see when we talked about stable and unstable directions, so we always have this plane which is codimensional with the flow. So there exists always a Markov family rectangles like this. So we always have stable and unstable local manifolds like this, which are transverse. So it will form a rectangle, and it will be transversal to the flow. Okay. So this Markov family is interesting. In fact, it will enable us to study to code our dynamics. We will see how. So, in fact, if we consider this Markov collection, so it means that any orbit, if we have this point x, and this will be the orbit of x, as we already see a little simple idea at the beginning. So this is the orbit of x, and in fact, it means that the orbit of x will meet infinitely many times in the future and in the past our Markov collection. So once we fix this Markov collection of rectangle, we can reduce our problem in a lower dimensional case, because if we look at the first return map, in fact this is x. So the point x, this is the orbit of x. So when we first meet our collection, at this time, it is t of x, and it's the first time where we meet our collection. So that t here it is the first return map of our collections, and r is the first return time, because in fact, this is the time, the r of x is the first time that the orbit of x meets our collection of rectangles. So this union of all these rectangles, we will call it x, and we will see what we will name these three things in the next slides. So as we said, our axiom A flow, yes. So our Axiom A flows, we have, it exists a Markov collection of the hyperbolic set of the Axiom A flow, and we can obtain a symbolic representation of this flow in using the idea here, because if we consider a matrix n times n, 0, 1 entries, such that the matrix is defined by, we have 1 if the interior of if we have two different rectangles, if the interior of the T of the first intersection to the second is different from phi, it means that you are here and you can arrive to another rectangle, so it will give 1. Otherwise, it will give 0. So if we take all the sequences such that for all n we have a omega n plus 1 equal 1, then we consider this set, and on this set we consider a shift map which is defined by theta of omega n plus 1. This set together with the shift map we call it subshift of finite type. And we endo this subshift of finite type by a metric D, which is defined the distance between two elements in this subshift of finite type. It's equal to the exponential minus the m, which is the greatest integer, such that omega I, such that omega I equal to omega prime I, which is less than m. So later, we will also define what is a cylinder. We will use it later. So if we take two positive integers, q and q prime, and sequence of alphabets A of symbols. So we define a QQ cylinder by C minus QQ prime. It's just to say that we have two-sided cylinders, because there's cylinders which are C0 n. So we have two-sided cylinders, and it's related a little to stable and unstable directions, in fact. So it's the set of elements in the subshift of finite type, such that omega minus q equal a minus q till omega q prime equal a q prime. So how we could, in fact, if we consider this map, which is defined in this sense, from the subshift of finite type to our x, which was defined here. So the system xt will be isomorphic to a subshift of finite type. In fact, this is very useful, because any element in the space x will be coded by an element in the subshift of finite type. So this diagram is also equivalent to say this. So if we have a point x and x, small x, it will be equal to chi omega in the subshift of finite type. And we also, if we have a Gibbs measure, if we consider the Gibbs measure on the subshift of finite type, we have mu x, which is defined by this isomorphism. It will be a measure on x. So this is how we'll identify the measure on the x. In fact, the x that we have seen here, this is called a Poincaré section. So now our flow GT can be represented by a special flow over the system xt. And this x, it will be the Poincaré section for the flow. The r, we will see why it's called height function. In fact, the r here, it was the first return time of a point x. So the function r is the first time. So because if we start from a point x here by the flow, so we are moving like this until we meet for the first time again the section x. When I say meeting the section x, it means meeting one of the collection of rectangles we have seen. So the first time that we reach, it will be r of x. For example, if I continue, the first time I will reach again the section x, it will be rtx. Okay? So, and that's how we continue. So this is the definition of the first return time function, which we will call later height function for this special flow. And the Poincare map T, what we have seen here also. So this map is defined by T of x equal GR of x. In fact, the flow is continuous time, but the map T maintenant, it will be in discrete time because we are taking just the time when we arrive to the sections. So T of x it's the position of the flow at the first return time of the x into the section x. So what is the suspension flow? As we said, the axiom A flow is represented by a suspension flow over the space xt. So to present this, in fact, we consider the space xr. It will be here. I will describe what it is. So we consider all the couples xs in the Poincare section x times r, whereas the time s it's between 0 and the return time, first return time of x, where the points x r of x and tx 0 are identified. What does this mean? In fact, this is the space. So if we start from x0, normally we start from a point x, and by the flow g, we have gt of x. So in this space, a point x is identified by x0, the initial time. So by the flow gt, we are moving. So at time t, it was here x0, it will be x, but t. So it will be like gt of x0. Okay? So we will continue by the flow as we saw here. We continue until we reach the section for the first time. So the first time I will reach the Poincare section, it will be the time r of x. So it will be the position x with the time r of x. Okay. So this point now, it will be identified by tx0. This point here is identified with this here. And again, we move with the flow until we reach, again, the Poincare section. When I say Poincare section, it means one of the rectangles. So when I reach here, it will be t of x, but now the time, it's the first return time of t of x. So it will be rt of x. And I continue in this way, okay? So in this way, I can define the suspension flow for a couple xs. It will be, so if I continue in this way until we have the time s, until before reaching s, so it will be t n x, but this n, it's not any m. It will be t n x, it will be s plus t, so s plus t minus s n r of x. This is the, I don't know if you have seen before, this is the ergodic sum of a function. So the ergodic sum of the function r of x, it's the sum from 0 to n minus 1 ti of x. So I forgot, it's rti of x. So sorry, this is r. So in fact, this is r of x plus rt of x plus rt2 of x until plus rtn minus 1 of x. And it's logic because here this point is identified again by t2x and r of t2x, r of x plus t2 of x. So this flow will be defined as follows, and in a condition that this n, it's the unique non-negative integer such that s plus t here, because we have to satisfy this condition to be in this space. So this s plus t here, it must be strictly, it's strictly less than Sn plus 1 r of x and Sn r of x. In fact, this is like the discrete time, and this is the continuous time. So between 0 and s plus t, we have a discrete time until a little interval which will be continuous. Okay. So now the description of the Z-extension of axiom A flows. So we will consider a Riemannian manifold until, because we were talking about an axiom A flow in general. Now we want to work with an infinite measure. So that's why we consider a Riemannian manifold with sigma finite measure, mu tilde. So it's defined in a way to be an infinite measure. So we consider the same example as we've seen before, just to see geometrically how it is. So the extension is defined in this way. If we take phi, a map from x to z, so the extension t tilde on x, z is defined by t tilde of x m. It will be tx. So the map, so normally with the map, with the Poincaré map from x, it will be tx. But because we are working now in an infinite measure, so starting from position m, so the phi here, it will indicate the changing of the position. And this, if we consider this as cell, so if I start here, t tilde of xm, so it will be tx m plus phi of x. So this is the extension. In this we can identify the extension because we are changing the cell here. What I mean cell is because we have several copies of the same manifold. So this will indicate the position in which copy we are. So just to see what will happen after n iterations of the map. So for example, t tilde 2, if we apply again t tilde of 2xm, it will be t2x, and m plus phi of x is already there because in fact I have to write it's t tilde of tx m plus phi of x, and again it will be t2x m plus phi of x plus phi of tx. So if we continue in this way, we will have t n x m plus phi of x plus phi t of x plus phi until phi t n minus 1 of x, and this will be the ergodic sum of the function phi. So this is the extension. It's defined like this. Okay. So now we will, to prove before saying our results, we will use this local limit theorem to prove our results. In fact, it's called local limit theorem because in fact we are looking locally, because it may be viewed as a double local version of the central limit theorem. Why it's local? Because first we are looking at the probability that S and phi equal to 0. Just to say something, our goal is to study the first return time. So if I start in this cell, for example, my goal is to return back to this. For example, if I consider a point x here and a neighborhood around this point, I have to return back to the cell and to the ball of x. So when I say returning back, it means that I must have that m plus sm phi of x equal to 0. I have to return back to the initial cell. So it's local because I have to study the probability that S and phi equal to 0. This means that I return back to the initial cell because the phi indicates the extension. While the classical central limit theorem is only concerned with the probability that S and phi is less than or equal epsilon radical n. Second, it's local in the sense that we are looking at the probability conditioned to the fact that we are starting from a set and landing on other set. We will use this in fact, because we will return back to a neighborhood of, we return back to a set, we can say. So that's why it's local. We proved the following. So the proposition there exists a constant positive. So there are some integers such that with certain conditions, such that for any cylinder, Q prime, two-sided cylinder of the subshift of finite type, and any measurable set of, in fact, sigma plus A is just the one-sided version of the subshift of finite type because this is two-sided. So we have that the measure of starting from a set C intersection that S and phi equal to 0. That means that I want to be in the cell, the initial cell, and theta minus and theta k to P minus 1b. It means P minus 1b just to say that I am again in sigma. Okay, because P it's from sigma to sigma plus. I forget this is plus. So this the measure of this set minus the measure of C, measure of B over radical to pi radical angle, it's less than or equal a constant times the measure of B, measure of C divided by N. So we have, in fact, we have N here and radical N here. This is related to the fact that we are doing a Z extension. Z extension, it means in dimension 1, because there are other cases where we have Z2 extension. In this case, we will not have radical and we have N, or it's different. So we will see how we will use this local limit theorem. So the results, as we said, our interest is study the time needed for the flow to return back to an epsilon neighborhood of its starting point. So if I consider a point y, if I consider a point, I have to write y here, and y here. Okay. If you consider a point y in our M tilt, so we define the first return time for the flow. This time is continuous, so it's the first time strictly greater than 1, such that gt of y is in the pole of center y radius epsilon. So studying the asymptotic behavior of this return time, we obtain the following result, that the limit of when epsilon goes to 0 to log radical tau epsilon over minus log epsilon is equal to the Hausdorff dimension of the measure minus 1. Okay, I will present just something that I will use later for my proof. In fact, this proposition is just to be used at the end to prove this. So in fact, for an axiom A flow, we have always the Lyapunov exponents, the stable and the two Lyapunov exponents, lambda s and lambda u. And we said that for an axiom A flow, we have the local stable manifold and unlocal unstable manifolds. So if we have an x in lambda, we said that we always can code this element by an element omega in the subshift of finite type. So we define LMS, and these are just quantities which are the length of the stable and unstable manifolds passing by X and contained in the cylinder, in the two-sided cylinder C minus Mn, which is containing X. So just to make some relation between Lyapunov exponents and these expansion rates of the stable and unstable leaves. In fact, if we define, this is well defined by the ergodic by the Birkhoff-ergodic theorem. These limits are well defined, and we proved a proposition that they are related with the Lyapunov exponents by these formulas. So we have that the Lyapunov exponent is equal to the expansion rate of the stable leaf divided by the integral of the proof function. I just want to return back and why we say that it's a height function. We said that it's a height function, or maybe sometimes you say it's a roof function, because we see that it's the roof. It's like the roof function because it's where we reach to the Poincaré section at every moment. So these formulas are useful later. So how to prove the pointwise convergence theorem? So we fix epsilon positive as positive. Any point y in empty, it's represented by sx en fait. So it's gs of x, which means that it's the position x at time s. Okay, and we said that always this element x is coded by an element omega in the subshift of finite time. We consider the ball of radius y, radius epsilon, and center y. So what we will do, we have our element is in the manifold, and what we will do is projecting this ball on the Poincaré section. So if I don't have a picture, imagine that we have a point here, not here. We point here and we have a ball. So we will project the ball, the projection of the ball on the Poincaré section. So we have the projection of a ball. It will be included by and contains a ball. So the projection of the ball of center y, and this y, it's the representation of xs. It will be between the balls if we take k, the constant Lipschitz of the projection map. So it will be between these two balls of center x and radius k epsilon over k. And now what we will do, now we will define, we have the projection of the ball. Now it's on the Poincaré section. What we will do is we will define a return time now to the map t tilde. We know that the map t tilde is defined on x tilde times z. This return time is in discrete case now. So we will define the first return time of this map into the projection of the ball in this way. So the return time will be the minimum discrete time needed such that tk of x is in the projection of the ball, and because we want to return in the initial cell, we have to say that this ergodic sum is equal to 0. It means that we will return back to the projection to the ball and in the initial cell. And so now we have two return times. We have the return time of y and the return time of x, if you want. So if we recall the definition of the return time to epsilon, it's the return time of x with the map t tilde. In fact, they are related in this manner. So every y in the manifold, it's the representation of xs in the suspension flow, such that the y is equal to gs of x, and the s, it's strictly less than r of x, because we are working in the, because we said that an axiom A flow can be represented by a suspension flow, and that's it exactly. Okay, so for almost every y element xs, the return time to epsilon of y, we can see a little sketch of the proof. So the return time, it's equivalent to the return time on the Poincaré section x times the integral of the roof function d mu of x, which is the measure of the on the set x. In fact, the proof is that because the return time of y plus s, it's like t plus s, as we've seen before. It's between the sum, because in fact I need a picture. So if we have a y here, so to return back, I need, I don't have a precise picture, because the return time, we will imagine this is t plus s, and we know on the suspension flow this is strictly less than Sn plus 1 r of x and Sn r of x. Imagine that t now it's our tau epsilon y. It's it's T. So in fact, the n here, the n, it was the discrete number n. So it will be so that T plus S, it will be strictly between S n, but the n here is the return time W epsilon of x, because the W epsilon of x is the first time that we return back to the projection of the ball. It's in the discrete case, W epsilon, okay? So we can easily verify this, and using this, after we can use the Birkhoff-Ergodic theorem, which says that for almost every point x, we always have that the limit of when n goes to infinity, 1 over n, the sum, the Birkhoff sum of a function here is equal to the integral of this function. So using these two formulas, we can deduce this by little calculation. It's not very difficult. But this is very important relation, because we have a relation between the return time of y and the return time of the ball of center y radius epsilon, and the return time of the projection of the ball on the Poincare section. And on the Poincare section, I have a t, which is in discrete case. And in discrete case, it's easier to study the return time. So, in fact, what we will do, we had the ball of radius y and center radius epsilon and center y. We projected it into the Poincare section, and we said that this projection is contained and contains a ball. And then what we will do is we will prove, which there are several lemmas that we proved. And at the end, we have this, that the projection of the ball, which is contained in a ball, this ball, under certain conditions, on taking into considerations the stable and unstable local manifolds, the length, and all of these conditions, we can prove that this ball is contained in a cylinder, in a certain cylinder. P epsilon and P prime epsilon have to have certain conditions also related with the radius here. And we also can prove under certain conditions also that this ball contains a cylinder. So what we prove is that the projection of our ball is contained and contains a cylinder. In this case, what we will do, we will define a return time for a cylinder now. So we can study the return time for the cylinder, and deduce the return time on the Poincare section X, and using the relation that we said here, we can deduce the return time for our flow. So that's the idea. So proving the results for T epsilon will be done by studying the asymptotic behavior on the Poincare section, and which is deduced by the return time on the cylinder. So this is the sketch of the proof. So we define the first return time into a cylinder by the minimum m, such that we always have to return back to the initial cell, and such that, so this is the shift map on the subshift of finite type, because the cylinders are defined with elements in the subshift of finite type. So as we use the flow for the manifold, we use the Poincare map T on the Poincare section, and on the subshift of finite type, I use the shift map. And we've seen that there is a relation between T and theta. So the relation between T and theta, it's because of the isomorphism here. Okay. So for example, T of something, it's equal to chi of, this sigma is theta, sorry. So there is always a relation between T and theta. So we will denote a set, which is the set of points for which n is a return time to the cylinder. So it's all the elements which will return, the elements of the subshift of finite type which will return back to the cylinder. Okay, so we have that the return time of the cylinder, it's minimum m such that the omega is in this set. So, um, so now we will define just, we will set, you can see what is the entropy. We will use it just to prove our theorem at the end. If we consider H the entropy of the subshift of finite type, we proved two lemmas. So we proved that under certain conditions relating A and B with the entropy in this way, we can prove that for a sequence Qn at Q prime n, this satisfying this, we have almost surely that limit n when n goes to infinity to log radical to the return time to the cylinder Qn prime divided by the length of the cylinder, it's greater or equal 1 over 2a plus b, and the second lemma is the same, less than or equal for the limits. In fact, proving these two lemmas will help us to prove our theorem. These two lemmas are for the are studying the asymptotic behavior of the return time to the cylinder. So now we have certain conditions, in fact, but the idea is to say that the measure of a set, and this set satisfy certain condition that we have the element and the subshift of finite type such that the cylinders, and this is the element of that such that the cylinders satisfy this condition, that its measure it's between exponential minus h plus delta exponential mod. This condition will help us in the proof. So the measure of the cylinders satisfying these conditions with this set, which is the elements where n is a return time. Okay, if we calculate the measure of this set, so it's the measure of the elements in K and delta such that S and phi equal to 0 and theta n is in the cylinder. We just write the definition. So this is equal to the sum of all the cylinders in C delta minus Q n prime, because we are in this set. It's the sum of the measure of C intersection. It's just the sum. So you have the measure of this is the sum of the measure. Now the most important is using the local limit theorem. So now you can use the local limit theorem that we defined here, and we can prove that this is less than or equal. So this is less than or equal some calculation, and at the end you will see that it's all of the sum of these cylinders, mu of C 2 over radical n, and mu of C, it satisfies this condition. So at the end, we will prove that it's equal to 1 over n with this power, which is greater than 1. So you can deduce that the sum of this measure is finite. So by the Borel-Cantelli lemma, we can prove that if n large enough, then the elements here, because it converges to 0, then the measure of the elements here are strictly greater than n, because normally the elements here are the elements where n is a return time. So once you prove that this measure is 0, then the return time is strictly greater than n. It's not n. So we can use this implication just to, in this implication we can prove, in fact, the lemma. It's easy here to deduce that. So we prove similarly the lemma 2, and the idea is to relate these two lemmas. So we have the two lemmas, we use it in here and here. And the most important is using the relation between the return time of our flow and the return time on the Poincare section. So this is the relation, and using that, the inclusion of the balls, we say that the projection of the ball is contained and containing a cylinder, then the return time is between the return time of two cylinders. But yes, we've seen that here it's the written, it's the cylinder P epsilon P prime epsilon, so it will be just the written time, it will be here. Okay, so using all of this together, you can deduce by calculation that we have this limit, which is equal to, under certain conditions, equal to this. And now we will go back to the relation that I have introduced between the Lyapunov exponents and the expansion rates of the stable and unstable leaves. And there's a formula which is known for Abramov's formula. So this formula, together with this relation, we can deduce that the limit of log radical to epsilon over log epsilon, it's equal to this quantity. And the relation here, we can deduce this. And in fact, this there's a reference that say that this limit coincides with the Hausdorff dimension of the measure minus of the measure mu, which means the dimension Hausdorff dimension of the measure mu of the flow minus 1. So that's how we prove the pointwise convergence theorem. And another result, it was the convergence in distribution, but I didn't put the proof because I know it will take a long time. So for the convergence in distribution, what we will do is we will take a disk which is centered on the element y tilde in m tilde, which is transversal to the flow and orthogonal to it at y tilde. And then we will consider the sectional measure, which is defined in this way. So what we will prove is that the family of random variables mu0 tilde of the ball of center y radius epsilon square times the return time, it converges in distribution with respect to any probability measure, absolutely continuous with respect to mu tilde as epsilon goes to 0, to now we have sigma square flow, which I introduced. It's in fact the asymptotic variance of the phi, which is responsible for the extension, divided by the integral of the roof function, where these are two independent random variables. This follow the expansion distribution of mean one and follow the standard Gaussian distribution. So I can finish like this. There is application for geodesic flows. You can see it. You can see my paper and you can see the application for the geodesic flows if you are interested. And thanks for your attention.